Today we are going to introduce one of the major categories of transistors, bipolar junction transistors. Bipolar junction transistors, or BJTs for short, were the first type of transistor created. They are three-terminal devices composed of alternating regions of P and N-type silicon. The base, abbreviated B, controls the flow of current through the other two terminals. The emitter, abbreviated E, is the terminal that emits the primary charge carrier into the transistor. For instance, in an NPN transistor, which we will introduce shortly, N-type silicon is the primary component. N-type silicon has free electrons, which makes electrons the primary charge carrier for an NPN transistor. This means that electrons flow into the emitter of an NPN transistor. The collector, abbreviated with a C, collects primary charge carriers as they come through the device. For instance, in an NPN BJT, electrons go out the collector. There are two types of BJTs, NPN, which we already mentioned, and PNP. The letters indicate the layering of P and N-type silicon within the device. In an NPN transistor, two regions of N-type silicon sandwich a single small region of P-type silicon, and conversely, in a PNP transistor, the opposite is the case. The middle layer is connected to the base and is very thin, much thinner than is shown here. In an NPN BJT, the collector is connected to one N-type region and the emitter is connected to the other, and the same is true for the P-type regions in a PNP transistor. If you notice, the region connected to the emitter is more darkly shaded. This is to indicate that that region is more heavily doped than the other two regions. This means that the emitter has more free charge carriers than the other regions. We will see the implication of this when we discuss transistor behavior shortly. On the right, you see the symbols for both types of BJTs. The two are distinguished by the direction of the arrow at the emitter terminal. The arrow points in the direction of current flow under normal operation. For an NPN transistor, we said that electrons flow into the emitter, which means that current, i.e. positive charge, flows in the opposite direction. Hence why the arrow points out of the emitter for an NPN BJT. We are now going to look at how an NPN BJT behaves as different potentials are applied across the terminals. The diagram currently shows an NPN transistor with no biases applied over any terminals. The depletion regions at both PN junctions are shown, along with a depiction of the relative magnitude of free charge carriers in the three different regions. As you can see, the emitter side has many more free electrons than either free electrons in the collector or free holes in the base regions. This is due to the higher doping previously mentioned. If the base emitter junction is left unbiased, or a potential less than the turn-on voltage of the junction is applied between base and emitter, the depletion region still exists, and so no current flows. If we now set the base emitter voltage, or VBE, to be greater than the turn-on potential, then the depletion region between base and emitter disappears. The positive potential at the base attracts, or alternatively the negative potential at the emitter repels, the free electrons in the emitter region towards the PE junction. This leads to a large concentration of free electrons at the junction. Some of these free electrons will cross into the base region and recombine with the free holes and cause current to flow from base to emitter. Due to the low doping of the P region, however, there are relatively few holes available to combine with the free electrons, and so the size of the current from base to emitter is small. This covers the two major options for the base emitter region. Assuming the base emitter region is forward biased, there are two potential cases of interest for the biasing between the collector and emitter terminals. The first is when the potential across the collector emitter is larger than the potential across the base emitter. In other words, the collector is at a higher voltage than the base. Since the collector is at a higher potential than the base collector PN junction is reverse biased. This causes the depletion region to increase. Relative to the emitter, however, which is at a lower potential than the base or the collector is at a much higher voltage. This large difference in potential means that a strong electric field exists between the collector and the emitter. This strong potential, which attracts free electrons in the emitter towards the collector, combined with the small size of the base region, causes free electrons from the emitter to travel into the collector and for current to flow from the collector to the emitter, despite the existence of a depletion region between collector and base. Due to the relatively low doping of the base compared to the emitter, the current flowing from the collector to the emitter is much larger than the current flowing from the base to the emitter. The second case of interest is when the collector potential is higher than the emitter, but less than the base. In this case, the base collector P-N junction is forward biased as the P side, the base, is at a higher potential than the N side, the collector. This means that the depletion region between collector and base is mostly or completely gone. With no depletion region between either junctions, there is an easy path for electrons to flow from emitter to collector. Since the size of the potential difference between collector and emitter is less than the previous case, assuming a fixed base potential, the actual amount of current flowing from collector to emitter is less. As with other electrical components, there is a water flow analogy for BJTs. We will consider the model for an NPN transistor here. In this model, there are two movable arms that are connected together. When no water is flowing into the base, the bottom vertical arm is closed against the base tube by the VBE biasing spring. This holds the top horizontal arm in place and prevents water from flowing from the top to the bottom, i.e. from collector to emitter. When enough pressure to overcome the VBE spring is fed into the base, the bottom arm is pushed open. This allows a small current to flow in through the base. It also pulls down the top arm, allowing water to flow from collector to emitter. The potential between collector and emitter dictates the rate of flow once the arm is open. If there is only a small potential, then there will only be a small flow. The flow rate will increase as the water potential increases until it reaches the maximum flow permitted by the geometry of the system, at which point further increases within reason will not increase the rate of flow. From our discussion so far, we have identified three main operating conditions, or regions, for BJTs. Which region the transistor is in depends on the voltage across the base and emitter and the collector and emitter. The graph here shows what are known as characteristic curves for the BJT, base emitter on the left and collector emitter on the right junctions. Both graphs show the current into the base or collector terminal relative to the voltage across the junction. In the case of the collector emitter, the current through the collector also depends on the current into the base, and so multiple lines are shown for different example base currents. Starting with the base emitter junction on the left, if the voltage across the junction is less than the threshold voltage of the junction, then the depletion region between base and emitter still exists, and no current flows either from base to emitter or collector to emitter. This is known as the off operating region. The transistor is in the off region whenever VBE is less than VT, regardless of the collector-emitter voltage. If the base emitter voltage is greater than the threshold voltage, then the base emitter junction is on. The operating mode now depends on the potential across the collector and emitter. If the collector-emitter voltage is approximately greater than the base emitter voltage, we are in the first case we discussed, and the transistor is said to be in the active region, where a relatively fixed amount of current flows through the collector for a given fixed base current. If the collector-emitter voltage is less than the base emitter voltage, we are in the second case, and the transistor is in the saturation region. In this region, the current is approximately linearly dependent on the voltage between the collector and the emitter. We will discuss how to model and make use of these behaviors in the future.